So let's start this last talk of this morning session. I see that one of the co-authors, next student, Sarah Passiflora. So that is Elena Wang will talk about distance for geometric graphs via labeled March tree interleaving distance.
Thank you for the introduction, and thanks everyone for being here, and thanks to the organizers for giving me the opportunity to talk today. So today I'm going to talk about a distance for geometric graphs using the labeled merge tree interleaving distance. And this is joint work with Liz Munch and Chambers, who I believe are in person with you, and Sarah Percival. So our initial motivation is that given two embedded graphs, how can we efficiently compare them? It has been proven to be a difficult and computationally expensive problem. However, there are some practical uses of studying this. So below are three examples of embedded graphs. The first one is a set of two reconstructed maps of Berlin. So if we compare and somehow quantify the differences of two road maps from different time period of the same city, then we can tell how the city has evolved and changed over the time. And the second is a green fluorescent protein. By studying such embedded graphs, we can study its protein function. And the third is a handwritten character. If I were to ask a person what letter this is, you might tell me it's clearly letter A, but how can we tell a machine to recognize these things? And these are all useful applications of studying embedded graphs. So in my talk today, I'll first give some background on embedded graphs and some existing distances, as well as our topological signature merge trees. And then I'm going to go through our distance method as well as an application at the end. So what is an embedded graph? A graph is composed of a set of vertices V and a set of edges E. What makes it embedded is that it has a continuous function phi that maps the graph to a real space while dimension is greater or equal to 2. And that map is homeomorphic onto its image. So let's recall the definition of homeomorphism. It's a continuous bijective map whose inverse is also continuous. In an embedded graph, each vertex is mapped to a point, and edges are mapped to curves in the real space in such a way that the graph structure is maintained. In the remaining of my talk, we'll be focusing on our graphs embedded in R2 that are plane graphs. So now it's important to point out the difference between an embedding and an immersion. So in embedding, which is the set of graphs that we're considering, every edge crossing is a vertex. So for example, here, there must be a vertex at the crossing of these two diagonals. And in immersion, we remove that requirement. So it doesn't have, it only needs to be locally homeomorphic. So this does not require a vertex. So there have been some existing, sorry, I take that back. Now we have two embedded graphs, G and H, in their own sets of vertices and edges and their maps phi. We want to compare them. So we want to ask questions such as how similar / different are they? And what does it mean to be similar? Both of these questions don't have definitive answers, and they're just really application specific. So we want to explore these questions through this study. And in this work, we also assume the two graphs not only to be embedded in R2, they're also pre-aligned, because graph alignment is a very difficult question on its own right. So for the existing distances, they all have their own pros and cons. So we want to develop one that captures the outline of the graph and is computable in practice. Yeah, so these are some examples of existing distances. The figures are courtesy of Carl and Wang. So first, it's the house roof distance, where we measure how much we have to thicken one graph to contain the other. And then below that is the Fauché distance, also known as the dog walking distance. We measure how long the leash has to be for someone to walk their dog. On the right, on the top, is the traversal distance. So as the name implies, you travel through the graph via the edges. And below that is a graph distance. So instead of matching edge segments, it's required to match the vertices and measure the distance that way. And these distances all come with their pros and cons. So for example, the Hausdorff distance really measures the geometry, but not the topology of the graph. And if we compare Hausdorff distance and Fauché distance, I can give an example where the Hausdorff distance is really quite small, while the Fauché distance is quite big. So for example, if we were to compare these two graphs, it doesn't have to, the Hausdorff distance is small because you don't have to thicken the graphs so much for one to contain the other, but the Fauché distance will be large. And on the right here, we see that we're actually comparing the same set of two graphs, G1 and G2. So their traversal distance is really quite small. It's just this segment right here. However, their graph distance is quite large, just because the nature of having to match the vertices. So as I mentioned earlier, that we want to develop a distance that captures the outline of the graphs. And therefore we picked merge tree as our topological signature. So I'm sure the audience is very familiar with the definition of merge tree, but I'm going to define it nonetheless. So it's a finite directed rooted tree that has one vertex that's designated as a root. So the root is the vertex here, labeled as R. And edges have a natural orientation. So in this example, I drew them upwards, but they can also go downwards. Both are options. And a merge tree is such a tree together with a height function on the vertices. So we map the tree to the real line, essentially, and all the vertices would have a height value, while the root vertex here gets a value infinity. So given a graph G, how do we build the merge tree? This is a spoiler, but for the rest of the talk, it's going to be in the context of directional transform. So everything that I'll be talking about will be given a specific direction of which we'll be building the tree on. So here, given this graph G and this direction omega right here, we can fix a height function for the graph along this direction. And then we can start building our merge tree by counting the number of connected components of the induced graph induced by the sublevel sets. So here, our first component is picked up to be the first leaf here. And when we move upwards on the height function, we find our second connected component, and thus it generates another leaf. And these two components merge at this point. And just slightly before they merge, we pick up a third branch. We notice that here, the triangle shape here in the graph is completely ignored in the merge tree. And that is because it's already part of the connected component. That's why it doesn't get picked up. And all components merge at this point, and then we build, this is our infinite tail at the end. And that's how we build a merge tree. So there have been many distances designed for comparing merge trees, but not many of them are computable in practice, or they might be very expensive to compute. So we restrict ourselves even more to the labeled merge tree setting. So a labeled merge tree is a merge tree together with a map that maps the integers 1 through n to the set of vertices of the tree, and it's surjective on the set of leaves. So looking at this example on the left here, we have this merge tree, and all of its leaves get one, but maybe not only one label, and a vertex that has degree 2 in the middle here, it could also get a label. So it's a label. with 3. And given such a merge tree, we can actually represent it via a matrix. So the induced matrix of a labeled merge tree is a matrix where its entries are the function values of the lowest common ancestors of the vertices labeled with its row and column numbers. Now, that's very long, but it's actually quite intuitive if I unpack the definition. So we first recall the definition of the lowest common ancestor, and that's just a vertex. That's the lowest vertex that is the common parent to 2 vertices. And in our setting, we say that a vertex is its own parent. So we notice that it's, first of all, symmetric. So we only have to care about the upper triangular matrix of this induced matrix. And on the diagonal, it's really just the height value of these vertices labeled with its row and column numbers. So for example, the entry 1, 1 here, we find the vertex 1, and because it's its own parent, so we populate its height as this matrix entry. And it's similar for the rest of the diagonal. And for the non-diagonal entries, for example, if I pick the entry 1, 3, we find the vertex that is labeled 1 and the vertex that's labeled 3, and we find their merge point, which is here. And we find that vertex height value, which is A4, thus A4 goes here. That's how we populate the rest of the matrix. Now, if we have 2 of these labeled merge trees that have the same number of labels, they will have the same sized induced matrices, and we can take their difference matrices. We can take their difference matrix and use their L infinity norm to represent the distance between the 2 labeled merge trees. So the L infinity norm of a matrix is the maximum entry of its maximum of the absolute value of all of its entries. And if we look at the example here, T1 is the same merge tree from the previous slide. And TB here, I just moved the merge point from A4 to A3. So how that's reflected in the induced matrix is that we notice all the entries that used to be A4s has now become A3. So naturally, if we take the difference matrix and compute its L infinity norm, we get absolute value of A4 minus A3. And that is the value that we use to represent the distance between these 2 trees. And this distance is defined by Gasparovic et al. And it's actually an interleaving distance. So next, I'm going to talk about the method that we used to develop our distance based on that context. So you might have noticed already that the entry-wise sum of matrices require them to be the same size. So it requires the labeling to be the same size, essentially. And that's not naive from any given of embedded graphs. So for example, G1 here has 1, 2, 3, 4, 5 nodes, and G2 here have 4 vertices. And at this direction, they're labeled merge trees. One has 2 leaves, one has 3 leaves. So they're all different sizes. So we want the same number of labels on each tree. And how do we do that? First, I want to explore which vertices that are important to us. And we discovered a vertex that we define, a set of vertices that we define as extremal vertex is especially important to us. So the definition of extremal vertex is that it's a vertex that is not in the convex hull of its neighbors. Let's just walk through this definition a little bit. So for example, in the graph on the left side here, V1 has 2 neighbors, these 2 vertices, and their convex hull is this straight line. And V1 is not in that convex hull, hence it's in extremal vertex. And on the contrary, once I added this vertex, once I added this edge right here, V2's neighbor is now these 3 vertices, and the convex hull is the triangle. And V2 is now in the convex hull, hence it's not an extremal vertex. So why are they important? It's important because a vertex in a graph only gives to a leaf in a merge tree for some direction if it's a extremal vertex. So take a look at this example here again. V1 gives birth to this branch right here at this direction. And V2 does not give birth to any leaf or branch at any given direction. And so this is the set of vertices that we want to label in our distance. So after we find the set of extremal vertices, we find the closest point to all of these extremal vertices on the other graph. So just take one as an example. So if we pick this vertex 7 from G2, we find its closest point on G1 via Euclidean distance. So it'll be this point right here. And we add a node on the merge tree that's associated with G1 on the same height. So it ended up getting mapped to this vertex right here. And we do that for all the extremal vertices. So G1 has 3 extremal vertices, so it has 3 blue labels, and G2 has 4 extremal vertices, so it gets 4 labels. And at the resulting labeled merge tree after the labeling scheme, we get 2 trees that both have 7 labels. So now thus far we've formulated our pipeline. So given the embedded graphs G1 and G2, we have their labeled merge tree T1 and T2, and then their induced matrices MT1 and MT2, and the distance between T1 and T2, and thus G1 and G2 at this specific direction is then the L infinity norm of the difference matrices of MT1 and MT2. So as I mentioned earlier, everything we're talking about is in the context of directional transform. And the reason why we care about that is because the merge tree changes when we change the directional input. So given the same graph and 2 different directions, we get 2 different trees. So for example, given G here, we pick the angle omega-1. On the left here, we get a merge tree that has 2 branches, that has 2 leaves right here. And after I just shift the angle to the left a little bit, we get a merge tree that has 3 branches. So these 2 trees are combinatorially different. And we want to observe when exactly does the combinatorial tree change. So we call these changes change point critical angles. So the critical angles are the normal vectors of edges. So going from the previous example, any angle that is in the wedge of this green wedge, we will get a combinatorial tree that has 2 branches. And this critical angle right here, which is perpendicular to this edge, is exactly the change point of when the combinatorial tree changes. So after passing that point, we move to the pink wedge, and every angle in that pink wedge would induce a merge tree that has 3 branches. And this is important for our main theorem of the paper, which if we define a function that takes the direction as the input and the L infinity norm between the 2 induced matrices obtained from the merge trees as the output, then F is piecewise continuous. So just to review the whole pipeline here, we have 2 embedded graphs, and at every angle we have 2 induced merge trees, and we compute the distance between these 2 labeled merge trees. And we do that for all angles from 0 to 2 pi, and we get this different distance graph. So the critical angles is when these jumps and discontinuity point happens. And this is important in practice because if the tree has the same combinatorial features, then we don't have to recompute the tree. We can just repopulate the induced matrices to compute their distance, which is much cheaper than having to compute the tree at every single angle. So finally, the definition of our directed merge tree is the integral of this distance graph over 0 and 2 pi. So now we want to explore a little bit how is this useful? What can this be used for? And is this a reliable distance in some sense? So we apply it to a Passiflora leaf dataset. So the dataset consists of 3,319 leaves from 40 different Passiflora species. Each data point consists of 15 ProQuest-aligned XY coordinate pairs representing 15 landmarks on each of the leaf. I'll zoom in a little bit. So these landmarks are chosen based on the biological structure of the leaves, and these are handpicked by some very hardworking undergraduates. So we very much appreciate their work. So what we want to do is that we want to differentiate each class using our method. So this is an example of how we do our computation. So we pick 2 leaves, and we only trace the outline of the leaves and ignore the inner vines that you saw in the previous slide. And that's because in the merge tree computation, these vines would get ignored anyways. So we just remove them altogether from the beginning. And given any set of 2 leaves, we compute the distance function, and then we integrate over the domain. So we sampled 1 leaf from each of the 216 plants that represent the mature shape of the leaves on that plant. And we computed pairwise distances between all pairs of leaves and constructed a distance matrix that's of size 216 by 216. And we used multi-dimensional scaling to realize this matrix. And on the left is our result. So in this embedding, we can see that the morpho classes A, B, and C, and even D are quite separated. And that's good indication that our distance is doing a good job of telling these different morpho classes apart. And on the right here, we see there's some more overlapping between the morpho classes E, F, and G. But if we take a look at the morpho classes on the right here, they're really quite similar to start with. So it was very difficult for our distance to pick that out, just because of the inherent similarities of the morpho classes. And on the right side, what we're comparing against is the PCA analysis that the original authors of the dataset did, in which they used the 15 landmarks as a 30-dimensional vector to perform the PCA analysis. So we actually see similarity in the separation, right? So the class A, B, and C are quite separated, and the morpho classes that are similar are quite have heavy overlap. So this is a proof of concept that our distance is actually doing something correct. So this is just a summary of our distance. It's good for summarizes the outline, outer shape of the data, and excels at pairwise comparisons. It's computationally cheaper than comparing the original data, say, than using graph distance, for example, which is NP hard. And it does have its own limitations. It can't summarize the internal structure of data, but that's inherent nature of the merge tree, so we can't really change that unless we pick some different topological descriptors. It requires the data to be pre-aligned, as I've mentioned before, and it's still quite expensive in practice, and that's something that I want to improve on in the future. So I would like to improve the computation complexity. I think I still have 1 minute. Yeah, so for those who are interested, currently it's O of n squared m squared log n. So the m log n comes from the merge tree computation. The n squared comes from populating the lowest common ancestor, the induced matrices, and the last M comes from the number of critical angles gotten from the number of edges. And another part that we're trying to do is to prove its theoretical results, including stability. So far we have a conjecture that says we think it's probably not going to be globally stable, but it will be locally stable within the critical wedges, because that's when the jumps of the combinatorial tree don't happen and when the labelings don't change either. And we also hope to extend it to R3 in the future and apply to more data sets such as cell morphology or embedded neurons. And these are all questions that I'm interested in exploring in the future. And lastly, I would like to thank my collaborators, Liz, Erin, and Sarah, and my amazing lab at MSU for such a supportive environment, as well as NSF for the funding. And the paper is in preparation and we hope to publish it soon. Thank you so much. I'm happy to take any questions.
Any questions? Yeah.
Hey, Elena, thanks for the talk. I was wondering how you, I'm a little confused where the extremal vertices came in. So is it true that you project one tree onto the other and vice versa, and that solves the correspondence problem?
Yes, exactly.
So where did the extremal vertices come in?
Right. So for example, in this labeling process, these two vertices are not extremal because they're contained in the convex hull of its neighbors. So they will never generate a leaf from any direction. So we just ignored it in the labeling scheme.
So it's just a removal.
That's right.
Yeah, and well, as a follow-up question, I guess you mentioned you do need alignment, I guess. So
Yes.
You just minimize overall all rotation.
Sorry, I missed the last part of your question.
Well, I guess so the in the persistent homology transform, they take like an NP model over all rotation, right? So you could just do that, I guess, to solve the alignment issue. So I think you mentioned on the last slide you need two shapes to be aligned.
Right, right.
So
Yeah, that's very important in this setting. That we require the embeddings to be aligned for this distance to be meaningful.
There's a question in the chat. I just repeat it, but you can read it anyway. Have you considered the Gromov Hausdorff distance or the Hausdorff-Yau distance? The former is fine and the latter is efficiently computable. And what is the relation between different distance you mentioned at the beginning, including the merge tree distances obtained by different directions/angle?
So I'll answer the first question. So we're actually in the process of applying different distances of the same data set and see what results we get. And yeah, as a subsequent step, we would analyze what kind of difference these distances would have to the same data set. That's a work that we're working on. And what's the relation between different distance you mentioned at the beginning? Sorry, the distance between graphs, is this the slide that you're talking about?
It's on Zoom.
Yes,
He's on Zoom.
Yeah. I don't think I understand I'm understanding the question.
It's probably on chat.
Yeah, so these distances, I've explored some of their differences, right? They just capture different features of the graph. Like Hausdorff distance captures the geometry, but not necessarily the topology. Hence, there could be big differences between Hausdorff and Fauché distance. And the traversal distance, is computable. It's, I think, mn OF mn log mn. But then it's not as fine as the graph distance, which is NP hard to compute. But does that answer the question?
It's on Zoom. So,
Yeah.
Maybe there was another question from the room. Question. So yeah.
So is your merge tree Yeah, can you reconstruct your graph from your merge tree, given all rotation?
I don't think so, because it ignores the inner structure. So if there's any inner structure, like for example, this triangle will never be picked up.
Even if you choose other better rotations.
Yes.
Yeah, it will further directions, but you can go this internal stuff. So if you had another like vertex in the middle of the other thing, so one of my other students, she could go, she's actually looking at it right now, if you have a lot of go back and
Thanks.
Any other, one more?
So if you have same number of order points, we ever consider the difference in the candlestick state?
I'm so sorry. I can't hear very clearly. Could you say it again, please?
If you have, for example, if you have two sets of same number of order points, have you ever considered, I mean, the distance in the candlestick state?
This- Oh, no, we have not considered other distances at the same angle, but that's also part of the future work that we've been discussing. No, thank you for the question. Yeah, that's a good point. We have thought about using other merge tree distances for different angles. Oh, sorry. Yeah, if that answers the question.
Okay, so if there are no other questions, let's thank Elena again.